Welcome to another Mathologer video. Today's video is about one of my own mathematical adventures, my quest to pin down the mathematically best ways to lace shoes. Yes, you heard right, the guy who only ever wears Birkenstock embarked on a mathematical shoelace expedition. This goes back to the time when my own kids were little. Teaching them to tie their shoelaces suggested to me to look at various mathematical aspects of lacing and tying shoes. Because of course that's the crazy way mathematicians think. We're always on the lookout for the mathematical soul of things, no matter how big or small. The whole thing started out as a bit of innocent fun, but then I obsessed a bit, happens to me quite a bit, and things got out of control. First I ended up publishing an article about the best ways to lace shoes, a bit of mathematical fun in the heavy-duty journal Nature, a fact which made the evening news on TV here in Australia, and resulted in a couple thousand of emails overnight and requests for interviews from all over the planet, believe it or not. 2 years later, I published a whole book about shoelace maths for the American Mathematical Society. That's my daughter Lara on the cover, well, her feet anyway. Lara's tying her laces. And that's me up there, in the corner, with hair. Anyway, time to get into it. So what's the best way to lace your shoes? Let's begin by looking at some familiar lacings. There, that's a mathematical shoe, a rectangular array of evenly spaced eyelet pairs. Looks comfy, right? A lacing consists of the same number of straight line segments as there are eyelets. And these segments form a closed path that visits every eyelet exactly once, just like in this first example. Now that's the crisscross lacing that most shoes come with. Here's the second most popular lacing, the zigzag lacing. And here are a couple of other examples. Weird, huh? That's a lacing that a friend of mine actually found in a French shoe shop a couple of years ago. Here's something else you've probably not seen before. And here's one that it's safe to say has never appeared in a shoe shop. Pretty insane, right? Well, don't worry, I didn't send my kids off to school with shoes laced like that. How about this one here? Well, seems to fit the bill, right? The lace forms a closed path, visiting every eyelet once. But do we really want to call this a lacing? Something's clearly not right. Can you pinpoint it? Well, the problem is there are eyelets that don't help with pulling the two sides of the shoe together, like this one here. Right? Doesn't do anything. So in a real lacing, we want at least one of the two segments of the path ending in an eyelet, those ones there, to connect to the other side of the shoe. Right, that lacing over there works. There are also extra special lacings like the two most popular lacings, the crisscross and the zigzag lacings. In these two lacings, every eyelet contributes twice to pulling the two sides of the shoe together. I call such lacings tight. In other words, in a tight lacing, every segment of the closed path connects to two sides of the shoe and there are no vertical segments at all. This has the effect that as you travel along the lacing, you constantly zigzag back and forth between the two sides of the shoe, like this. Okay, there, zigzag, 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 zigzag. Okay, down to work. I've shown you 5 different lacings for a shoe with 7 eyelet pairs. So let's list them all. Nope, let's not. It turns out there are more than 38 million such lacings. Almost 2 million of these are tight lacings. The number of lacings increases rapidly with the number of eyelets. For example, for gauze shoes with 100 eyelet pairs, we get in the order of 10 to the power of 354 different lacings. Now, the formula for the exact number of lacings is this scary looking monster here. Ooh. And my first challenge for the keen among you, determine the number of tight lacings of a shoe with 5 eyelet pairs. Remember, tight lacings are the ones that go back and forth. And the challenge for the super keen, what's the general formula for the number of tight lacings? As always, post your answers and ponderings in the comments. Okay, so we have our lacings, sort of. That means we can now ask which of all the gazillions of lacings of a particular shoe is the very best. Of course, there are many types of best. People often say French things are best, so maybe the French shoe shop lacing is best by default. Anyway, ignoring the French, I thought there were two natural interpretations of the word best to consider. First, the shortest lacing, and second, the strongest lacing. Make sense? Anyway, it was these two interpretations of best that I went for. Okay, so first, what is the shortest lacing of a given shoe? Easy, right? Just have a computer list all possible lacings of this shoe and figure out which one is the shortest. With 38 million lacings at a modern computer, that's definitely not a problem at all. However, even with 7 eyelet pairs, there are infinitely many different shoes to consider, depending on the spacing of the eyelets. Right? And of course, as true mathematicians, we are honor bound to consider all infinitely many different spacing of all the infinitely many different mathematical shoes. Shoes with just 2 eyelet pairs, 3, 4 pairs, etc. All right, for now, best means shortest. So what are the shortest ways to lace your shoes? Well, with all these infinitely many possibilities, you'd expect many structurally different shortest lacings. Not true. This came as a real surprise to me, but no matter the eyelet spacing, the shortest solution is essentially the same. First, the answer for the tight lacings. Remember, those are the lacings that zip back and forth between the two sides of the shoe. It turns out the shortest tight lacing is always the crisscross lacing. So the most popular lacing also turns out to be the shortest for each of those infinitely many possible mathematical shoes. Nice to know, isn't it? The first to prove this shoelace theorem was the mathematician John Halton in, 1995 in an article in the Mathematical Intelligencer, a couple of years before I got interested in shoelace maths. See, I'm not the only one. Now, what about general lacings? Here it turns out the absolutely shortest lacing is always what I call a bowtie lacing. Bowtie lacings have horizontal segments at the top and at the bottom, and the rest of the segments come in pairs, either making short parallel pairs like this, 1, 2, 3, or short crosses like this, 1, 2, 3. The basic bowtie lacing of a shoe starts with a parallel pair at the bottom, and then the parallel pairs and the crosses alternate. Okay? In the case of an odd number of eyelet pairs, like in the shoe over there, apart from the basic type of bowtie lacing, there are also these variations. There, and there. Obviously, since there are just a few segments shuffled around, all these variations have the same overall length. And so if one is of shortest length, then all of them are. Okay, so this is the situation for mathematical shoes with an odd number of eyelet pairs. For an even number of eyelet pairs, there is only one bowtie lacing, just like for the case of 6 eyelet pairs, this one here. And this particular instance of this type of shorted lacing also inspired the name bowtie lacing. Look, there's the bowtie. Okay, so I've told you the winners of the shortest lacing competitions, but how would we prove something like this? Well, most mathematicians presented with this task will place it within a whole circle of such puzzles known as the traveling salesman problems. Let's say you've got a number of towns, like for example all the major towns in the state of Victoria where I live. There, that's all of them. The traveling salesman problem asks for the shortest round trip that visits every one of these cities once. Here's the solution to this problem. And here's the solution of the same problem for more than 18,000 towns in Germany. Fantastic stuff, isn't it? And there is one very striking aspect of these solutions. Have a closer look. Can you see it? Yep, I'll bet a lot of you got it. There's no crossings. And that turns out to always be true. No solution to a traveling salesman problem will ever intersect itself. It's actually really easy to see that crossings can't happen. Just imagine if it did, then we'd have a closed path that intersects itself somewhere like this. Color the crossing segments like this. But now it's clear that if we replace both the blue and green parts by straight line segments, we get a shorter closed loop through all the points. That means any closed path with an intersection like this can always be shortened. And so the shortest closed path, the solution to our traveling salesman problem, cannot have any self-intersections. back to our shoes. What is the solution to the traveling salesman problem for a shoe? Yep, it's just the boring non-lacing loop that we stumbled across earlier. So how can insights about the general traveling salesman problem help solve our shortest shoelacing problem? Well, have a look at this lacing. Can this possibly be a shortest lacing? Doesn't seem likely, does it? And we can actually prove that it's not the shortest. We can create a shorter lacing just by doing a little bit of rewiring and straightening, just like in the traveling salesman problem. Right, there, straighten, and we've got something shorter. Okay, what about this new lacing? Can this one be the shortest? Nope, we can shorten again with some more rewiring. Right, just straighten out the green and blue bits. There, voila, once again a shorter lacing. What about this third lacing? Well, I'm sure you can guess, and here we go again. Okay, and shorter. Oh damn, no lacing, but we can fix that. All good. So finally, after 3 rewirings, we've ended up with one of our bowtie lacings. This rewiring idea was at the heart of my first proof that the bowtie lacings are the shortest. Very simple idea, right? But in the end, to completely nail down the proof, it was a bit tedious because of the ridiculous number of different cases that had to be considered. There, just to give you an idea, that's one of the diagrams listing the different cases in one part of the proof. Of course, I was pretty happy of having found my rewiring proof, but somehow my brain subconsciously kept working on the problem. And about 6 months after I finished the first proof, I woke up one morning in the middle of dreaming about another, much shorter proof. Now, pretty much all mathematicians have had dream proofs, and it's wonderful. You wake up really excited, and then 2 minutes later you realize your dream proof is completely ridiculous. Just like your dream of suddenly being able to levitate or co-starring in a movie with Scarlett Johansson. But amazingly, my dream lacing proof really worked. For the really keen ones among you, I'll illustrate a special case of my dream proof at the end of this video, proving to you that the crisscross lacing is the shortest tight lacing. Before that, let me show you some other really neat shoelace facts. Remember my shoelace book? Have a look at the subtitle. A mathematical guide to the best and worst ways to lace your shoes. Yep, I also pinned down things like the longest lacings among the different classes. I know, pretty strange, but totally the thing to do if you're a mathematician. Just like worrying about lacings with 100 eyelet pairs. And what turns out to be the longest tight lacings? Behold, the devil lacings. Pretty devilish, huh? Here are the devils for small shoes up to 6 eyelet pairs. And what are the longest lacings overall? Well, for short shoes, shoes with short horizontal spacing, the longest lacings are still the devil lacings. For long shoes, shoes with long horizontal spacing, those are the angel lacings. I've drawn the wings curved to make the pictures less ambiguous and more angelic. Fun, no? Well, I don't care. I think it's fun. But what about real shoes, I hear you ask? Like those on the cover of the book. Real shoes aren't flat, eyelets aren't points, laces aren't made up of line segments, and so on. Well, it turns out that the shortest lacings for ideal mathematical shoes are surprisingly robust and are also the shortest lacings for most real shoes. This is particularly true for the shortest tight lacings, the crisscross lacings. At least for any shoe I've ever owned, the crisscross lacing has always been the shortest tight lacing. But if you're really tired of my pure mathematical weirdness and you want to find out everything conceivable and inconceivable about real shoelaces, I've got just the site for you. You absolutely must visit Ian's shoelace site, which my friend Ian Figgin has been obsessing over for ages. Insane lacings, ways to tie laces, shoelace books, shoelace apps, etc. Yep, if I'm the pure shoelace nut, Ian is the applied shoelace nut. The weirdest thing is that Ian lives just a couple of kilometers away from me here in Melbourne. That definitely makes Melbourne the shoelace capital of the world, doesn't it? Now, your next easy challenge for the day: head over to Ian's website and find out whether you belong to the half of the people on Earth who are tying their shoelaces incorrectly. Intrigued? Okay, after meeting with Ian, we're definitely in good shape with the shortest and longest lacings. So what about the strongest lacings? Also, strongest in what sense? I'll postpone the in what sense and just start by telling you the surprising answer to the first question. What are the strongest lacings? It turns out that the two most popular lacings, the crisscross and the zigzag, are also the strongest lacings. For short shoes, like the one over there, the strongest lacing is the crisscross lacing. As you stretch the shoe, the strongest lacing stays crisscross, up to a certain changeover point. At this point, the crisscross lacing is as strong as the zigzag lacing. Stretching beyond the changeover point, the zigzag lacing is uniquely strongest. This basic behavior is the same no matter the number of eyelet pairs. Just the changeover spacing changes with that number. The more eyelets there are, the quicker we reach the changeover spacing. Okay, so you know the strongest lacings, you just don't know what strongest means. So I'll tell you. Have a look at this picture. See the pulley on the right? Ideally, a lacing is a pulley like this turned sideways. When a shoelace is tied, we assume ideally that the tension everywhere along the shoelace is the same. This tension then translates into the tension of the pulley in the horizontal direction, that is, the direction in which the two sides of the shoe are being pulled together. So, for a given tension throughout the lace, then the larger the horizontal pulling tension, the stronger we say the lacing is. Proving that the crisscross and zigzag lacings are strongest is super nitty-gritty and also only really become feasible after I had my dream. So let's talk about that now. To finish off, I want to show you my dream proof. Really quite special. A proof hatched in a dream that isn't completely crazy and actually works. That had only happened to me once before. In what follows, I'll focus on proving to you that the crisscross lacing is the shortest tight lacing of the shoe over there. This proof is completely general and works for any number of eyelets and any spacing. Anyway, on to proving that the crisscross lacing is the shortest tight lacing. What I'll do first is to just give you an outline of the proof. While I go over this outline, don't get hung up on any details. Just run with it and try to understand the gist of what's going on. I'll flesh out the details afterwards and things should come together nicely then. Okay, let's say over there, that's a list of all our tight lacings. Let's explode all of them into the different segments they consist of there. Explode, 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 and so on. We'll see that these segment collections resulting from the explosion of tight lacings share 4 easy to see properties. First, each collection consists of 10 segments. Second, each collection has at most 5 horizontals. I'll tell you the remaining 2 properties in a minute. Now, what we can do is to study these collections in their own right, to have a close look at all collections of segments that satisfy these 4 special properties. Why do that? Wait and see. I've named these special collections exploded lacings. Apart from the exploded lacings arising from real shoes, we see that there are lots of others, like for example this one here. The length of an exploded lacing is just the sum of the length of all its segments. This means that the length of a real lacing is the same as the length of its exploded counterpart. Pretty obvious, right? Now comes the nifty part of the proof and the whole point of this exploded stuff. Although there are a lot more exploded lacings than the real lacings we started with, it will be extremely easy to figure out what the shortest exploded lacing is. Why is that? Well, it comes from the overall lack of structure of exploded lacings, which makes them very easy to manipulate. The shortest exploded lacing turns out to be the explosion of the crisscross lacing, consisting of 2 horizontals and 8 short diagonals. It's also easy to see that the crisscross lacing is the only tight lacing consisting of 2 horizontals and 8 short diagonals. Consequently, Since the exploded crisscross lacing is shortest among all exploded lacings, the crisscross lacing must be the shortest real tight lacing. Really cool, huh? So my dream proof dodges all the complicated structure of lacings by taking a shortcut through some strange world of phantom lacings. How neat is that? Only in a dream. Okay, ready for the details? Ready or not? Here we go. First, let's give number labels to the different segment types that can occur. We'll call horizontal segments zeros. Next, we'll call segments that rise exactly one vertical step once. That's a 1 there, and that's another one. And you can guess the rest. The segments that rise 2 vertical steps are the 2s, and there are 3s, and finally there are 4s. 4s are the longest possible segments for our particular shoe. So, our crisscross lacing consists of 2 zeros, the horizontals and the top and the bottom, and 8 ones. The zigzag lacing consists of 5 zeros, 4 ones, and 1 4. Now, here are 4 simple properties shared by all the sets of numbers that correspond to lacings. First, as we have already mentioned, all these lacings consist of 10 segments, so there are 10 numbers, 10 non-negative integers. Second, the 4s are the longest possible segments, and so 4 is the largest possible number. Third, and again we already noted this, there will be at most 5 horizontal segments. That means we'll have at most 5 zeros. Fourth and finally, the distance between the top and the bottom of our shoe is 4 spaces. And traveling around the lacing, we must go at least once from top to bottom and back from bottom to top. This means that the sum of our lacing numbers is at least 2 times 4, that's 8. Okay, so let's call any set of non-negative integers that satisfies these 4 properties an exploded lacing. So for example, this is an exploded lacing. Let's check. 10 non-negative integers, tick. Nothing bigger than 4, tick. At most 5 zeros, tick. And finally, the sum of the numbers is 23, which is greater than 8, tick. Obviously, in a real lacing, there are at most 2 of the long 4 segments. So since our exploded lacing contains 4 4s, it cannot correspond to a real lacing. In fact, as I already mentioned, in the intro, many exploded lacings do not come from real lacings. Okay, getting there. Now, remember, the length of an exploded lacing is simply the total sum of the lengths of the segments corresponding to the numbers. For example, for our exploded lacing here, there are 3 zeros contributing the length of 3 horizontals. Add to that the length of a 1 segment, plus 2 times the length of a 3 segment, and finally add 4 times the length of a 4 segment. All under control? Easy enough so far, right? Okay, and now for the easy proof that exploding the crisscross lacing gives the shortest exploded lacing overall. 3 easy peasy steps. First, a shortest exploded lacing has sum exactly equal to 8. Why? Because any exploded lacing that has a sum greater than 8 can be made into a shorter exploded lacing by replacing some of its numbers by smaller numbers. For example, in our exploded lacing here, we can make these replacements. 2 plus 3 plus 1 plus 1 plus 1, that's 8. Now, second easy step. Because there are 10 non-negative integers that add to 8, they cannot all be 1 or greater. This means some of these numbers must be zeros, right? Let this sink in. All okay? Good. So that means a shortest exploded lacing contains zeros. Third and final easy peasy step. Okay, so maybe not so easy peasy, but it's not too bad, you'll see. Think again about our exploded crisscross lacing. It contains only zeros and ones. Now, can a shortest exploded lacing contain a number greater than 1? Let's see. In our example, there is a 3. Let's grab this 3 and one of the zeros and picture them together. Can you see how to shorten what we're looking at here? Yep, just a little traveling salesman rewiring and straightening. Here we go. There, the green is a 2 and the pink is a 1. This means that if we replace the 0 and the 3 in our exploded lacing by a 1 and a 2, we get a shorter exploded lacing, right? Also notice that the sum of the numbers in this new lacing is still 8. 1 plus 2 plus 2 plus 1 plus 1 plus 1 is 8. Can we shorten our new exploded lacing again? Absolutely. We can use the same trick to replace a 0 and a 2 with two 1s, like this. There. That's a 1 and a 1. Replace. Okay. Repeating the step once more, we can get rid of the other 2, the last number greater than 1. Go for it. Exactly the same step, right? 2 1s, replace. There. So now we're totally down to 0s and 1s. And this always works. We can always shorten until there are only 0s and 1s. And so the shortest exploded lacing overall must contain only 0s and 1s. But since the sum is 8, there must be exactly 8 1s and 2 0s. This means that the shortest exploded lacing is the exploded crisscross lacing. Ta-da! Pretty cool dream proof, huh? Well, actually, there's one more T to cross. Last thing we do. We've proved that every lacing consisting of 2 0s and 8 1s is a shortest tight lacing. And the crisscross lacing is definitely one such lacing, but maybe there are others. Well, let's see. Okay, time to play with our building blocks. What can we make with our 2 0s and 8 1s? Let's start at one corner eyelet. We must have exactly 2 segments meeting at that eyelet, and the segments must be different. So for that corner eyelet, it's clear that one of the segments is a 0 and the other is a 1. So one of the 0s has to be at the bottom. Similarly, looking at a top corner, the other 0 must be located at the top. But now our hands are forced. All we have left are 1s, and we have no choice in how to place them. There, and there, and there, and there. And that really finishes the proof. Very nice, isn't it? And as I said, it's very easy to adapt the arguments I just presented to also prove that the bowtie lacings are the shortest lacings overall. And my proofs of the strongest lacing theorems are also based on exploded lacings. So mathematical dreams can become mathematical reality. Who would have thought? And that's all for today. Pleasant dreams.